Hello everyone, today we're looking at an introduction to momentum and impulse, and I'm going to be kind of giving you guys a few definitions as to what these are, and then moving on to the examples in the Edexcel Further Mechanics book from the first chapter, examples 1, 2, and 3. Now some of you may be familiar with momentum already. Generally we refer to it as mass in motion, and you can think of it as sort of how powerful something is when it's moving. You think about a bowling ball moving slowly towards a set of bowling pins, you could probably get a similar momentum in knocking those pins over by throwing a cricket ball quite quickly at those pins. They'd cause both of them to move back. But if you push the cricket ball slowly towards a set of pins, you might not get all the pins moving down the same way the bowling ball did. So momentum is referred to or linked to two things. When we say mass in motion, momentum, sometimes given the symbol P, is calculated by how fast something is traveling, which is V, multiplied by the mass of an object. If you've got a heavier object, which is traveling at the same speed as a light object, the heavier object will have more momentum. Whereas if you've got two objects that are the same mass and one is traveling faster than the other, it will have more momentum. So momentum can simply be calculated by multiplying the mass and the velocity. And the units of momentum, very simply, are just the units of mass and velocity multiplied together. So the units are kilograms, meters per second. There is another unit as well, which we will come to momentarily. Now, impulse is an element that refers to how we can change that momentum. It's something which is given to an object which causes that momentum to change, i.e. to change speed, because generally the mass doesn't change of an object, so you're looking at how that speed changes. And this normally occurs by a force acting for a certain period of time. So impulse is given the equation force times by time. Now, if we think about force times by time, there is a formula that links force and time, and it actually comes from F equals ma, because a is technically the change in velocity over time, which is mv minus u divided by t. And if I rearrange that equation, we get ft is equal to mv minus mu. And this is a final momentum minus an initial momentum. And that is the same as ft, which means that impulse is also equal to mv minus mu, or the change in momentum, which simply means that the units of impulse are Newton seconds. And actually, those are the same units for mv and mu as well, just written in another way. So impulse has the units Newton seconds, but it technically could also have the units kilogram meters per second. So these are interchangeable. So this is our introduction to these two concepts. And what we're going to look at now are a few examples associated to this. Now, momentum and impulse are both vectors. So they do depend on the direction that we are dealing with. Well, I'm going to leave that there. I'm just going to bring up our two key examples for a second, where we have this over here. This is very simply just the first example in the textbook, example 1A, 1B, and then example number 2. So example 1 tells us about a cricket ball that is 400 grams and 18 meters per second. It's traveling at 18 meters per second. So very simply, if we want to work out momentum here, we are just multiplying the mass and velocity. But the mass needs to be in kilograms, so we do need to convert this to 0.4 times by the velocity, which is 18. And when you multiply those values together, you get a value of 7.2 kilogram meters per second. Very simply, on the next one, you've got 5 tons and you've got 0.3 meters per second. Well, tons in kilograms is 1,000, so that's 5,000 times by 0.3. And when you multiply that together, you very, very simply just get 1,500, again, kilogram meters per second. So very, very simply, just multiply two values together. Now, example 2, very, very similar situation. I've drawn a diagram to explain what's going on. You've got a 2 kilogram block that is set upon by a force of 4.5 newtons for 6 seconds. And it first wants you to work out the impulse. Well, we know the impulse is simply the force times by the time. The particle does start at rest. So if we think about I is equal to Ft, this is 4.5 multiplied by 6, which gives you a value of 27 Newton second. So what this is saying is that for those 6 seconds, we're creating an impulse of 27 Newton seconds. Now, if we want to work out the final velocity, as we do for the next part, we need to use this formula over here, which is that the fact that the impulse is equal to the change in momentum. So very simply, all we're doing here is substituting the 27, or I, is equal to mv minus mu. Well, we know the impulse is still 27. We know the mass is equal to 2. The final velocity is what we're working out. And the initial velocity was 0 because it started from rest. So actually, I don't need this. This is simply equal to 0. So therefore, if we divide 27 by 2, we can see the final velocity is equal to 13.5 meters per second. So very, very simple example, just applying our key formulae into this situation. Now, where this starts to become maybe a little bit more confusing for some people is when we come to the third example. Just kind of understand the basic elements when we look at these questions. Now, momentum and impulse generally refers to collisions because an impulse can only take place when an object is acted upon by something else. Now, in example number 3, you've got a 0.2 kilogram particle, which is striking a wall at right angles. Now, the reason we say at right angles is when it hits at right angles, it's going to rebound directly backwards at right angles. And it hits with a velocity in this direction of 3.5 meters per second. Now, if this is going to collide, the impulse needs to be causing a change in velocity. And it's going to rebound back afterwards with 2.5 meters per second this way, which means the force in this case, or the impulse, must have been in the opposite direction to its initial velocity. It must have been in this direction, causing this to therefore change its velocity to the left. Now, we said that both momentum and impulse are vectors, so it's very important that we get this understood, because when we're doing our equations, we need to make sure that we use the correct signs for this. Now, we know that the impulse is force times time or change in momentum. We aren't told about what the force is, we're not told about how long it takes, but we do know the velocities and we do know the mass. So we're going to be using mv minus mu. But we need to pick a direction to work with. Now, the impulse in this case we can see is to the left, which means we are going to make our direction to the left as our positive direction. If you do this to the right, you will still work out the impulse, but the value you will get will be negative, will be in the opposite direction. So very, very simply, we're going to say I is equal to mv minus mu. Well, v is equal to 2.5. So v is equal to 2.5, and u is therefore equal to minus 3.5 because u is acting to the right, it's acting in the opposite direction. So when we substitute these values in, we get 0.2 brackets 2.5 minus 0.2 brackets minus 3.5. And if you calculate that, you end up with 0.2 times 2.5 minus 0.2 times minus 3.5 gives you a value of 1.2 Newton seconds, or kilogram meters per second. So key thing here is just to ensure that you put these values in your diagrams, you identify which direction is positive, and generally it's the direction of the final velocity, which is different to our normal questions. Normally we look at the direction of motion at the beginning as positive, but for this, think about which direction the impulse is traveling in. Anyway, I hope that's made sense. If it hasn't, please leave a comment below or message me directly. Take care. Goodbye.